Unit 3, Lesson 8, Are They Similar? Okay. 8.1, Stretched or Distorted Rectangles. So we're staring at two rectangles, and the question they're giving us is, are these rectangles similar? Explain how you know. Okay. Go ahead and use the grid, all right, to kind of help with your reasoning. Write down your reasoning, and then unpause the video and see if we have the same thoughts. All right, so hopefully you pause this and you attempted to explain whether or not these rectangles are similar. So hopefully you use the grid. I realize that AB has a length of 1, as does EF, as does DC and HG, right? So all those sides are a length of 1 unit. Then I realize AD and BC have a length of 3. Meanwhile, EH has a length of 5, and FG has a length of 5. Okay, well, there definitely has to be a sequence of transformations, right? And use of a dilation, right, in order for this to happen. So we need a sequence, right? Sequence of transformations. And dilation, right? So let's see here. I agree that there's definitely going to be you'll have to use a translation of some sort to get Q down to R. I agree with that idea, but dilation's freaking me out because dilation needs a scale factor, right? Dilation needs a universal scale factor, right? So scale factor. So scale factor has to be applied to each corresponding side. So let's take a look at AB to EF. To get from here to here, 1 times what, right, gives me 1. 1, right? Like you have 1 times some scale factor, right, giving me 1. Well, that means your scale factor is 1. So this situation is here. Okay. But if I look at AD here, dilating to get me a 5. Okay, immediately I'm like, okay, something's wrong. Because 3 times what gives me 5, right? Division property. You should get 5/3. So immediately you realize we're not applying the same scale factor here, right? Like we're not applying the same scale factor. So are these two rectangles similar? No. All right. Dilation right here does not use the same scale factor. Okay, that's probably a good dead giveaway that something horribly wrong has happened in this situation. And even if you look at the title, right, it says stretched or distorted, definitely stretched, right? Like R is definitely being stretched like taffy horizontally, right? Um, Meanwhile, vertically, nothing's changing. Okay, so that happened. Now, if it was to be good, you would probably use the same scale factor across the board. Let's say they did use 5/3. Okay, your object 5/3 is like 1 and a little. It's like 1 and 0.67. So 6/7 is like right around here-ish. So your rectangle should have been somewhere looking like that instead. Okay, so immediately looking at it, it's like, yeah, that definitely did not happen. Okay. All right. So faulty logic. Tyler here basically has this huge instructions on making a proof that all rectangles are similar. And in this step, all right, he makes some false assumption, Why is it false? Let's try to go through this as best as we can. It's like it's equivalent to being like, all right, let's figure out what this crazy person is wrong about. When it's like, why they're crazy? Like they're you already said they're crazy. It's kind of like that. It's like when you ask somebody something and they try to explain or prove it to you, but like they're just not even talking about the same thing anymore, and you're just like, I don't think I can properly communicate right now. Um, oof. All right, so draw two rectangles, he says, A, B, C, D, and the other one, P, Q, R, S. Okay. Now, I'm going to draw another rectangle, and I want to make sure here that it is definitely not the same size. Okay. I'm going to try my best to do that. P, Q, let me go. P, Q, R, S. There we go. Okay. And okay, so we got number one done. So he does this. What's his name? Tyler. Okay. Then they say translate the rectangle ABCD by the direct line segment from A to P. Okay, what is that going to look like? So A to P is from that vertice to this vertice. Okay, let's do that. So we're going to translate over. A maps onto there. Okay. A goes on to P. Lovely. Um, let's figure out what else is happening here. And let's go ahead and give them the prime designations. We just moved this rectangle, so I want to make sure that I denote that. Okay, and now P, A prime and P prime coincide. That means they're existing in the same space in time. The points coincide because they're how defined in the translation. What he's saying is we moved from A to P, so of course A prime and P are going to coincide. Okay, so now this kid says we're going to rotate. Okay, we're going to rotate A prime, B prime, C prime, D prime by the angle D prime, A prime, S prime. If you look at that, D prime, A prime, and S is just this zero angle. Like it's not like this kind of angle. So let me try to figure that out. He says, rotate ABC by the angle now lies on PS. Okay, what is he wanting us to rotate around? I'm assuming he wants us to rotate around A prime, because that's the angle he's talking about. And then it says A prime, D prime now lies on PS. Okay, so rotate around. Wow, is he really saying like rotate all the way around? That doesn't make any sense. But he says A double prime, D double prime now lie on PS. A double prime. So is he talking about something like this? Let me get my. There we go. Okay. So A double prime, D double prime is definitely on PS. The rays coincide because it's how defined in our rotation. Okay, so this kid's getting a little shaky here. So let's see here. All right, so A double prime is definitely here. D double prime is still there. Actually, no, that doesn't make any sense at all. Because D would have to rotate. Okay, and all right, C double prime, B double prime's up here. Okay, so already this kid's getting a little messy. Dilate that new triangle using center A double prime and scale factor of PS to AD. So basically, he's saying we're going to make AD. Let me use a different color. Okay, purple. We'll use purple. So AD here, or A double prime, D double prime, is going to get to the same length as PS. That's what this means right here. All right, AD is going to basically get that big. And then now A triple prime, D triple prime coincide with PS. Okay. Okay. The segments coincide because A double prime is the center of rotation. A double prime and P don't move. And since D double prime and S are on the same ray from A double prime, then when we dilate D double prime by the right scale factor, what's the right scale factor, kid? All right, it will stay on PS, the same distance as A double prime and S. So S and D triple prime will coincide. Okay, that was weird. Okay, so what about the other sides? Like he didn't mention, like if he mentioned C, right? Because like all the other points, like notice how he doesn't mention all the other points. So I feel like he may have left that out, right? So that's step 4, right? He's basically launching out with that distance. What's unfortunate is he's leaving out some more details here. So the stuff in purple that I used to complete the rest of the rectangle is kind of an assumption there. Well, let's see what he does in the rest of the steps. I don't want to be that disingenuous to him. Because all angles are rectangle. Because all angles of a rectangle are right angles, meaning they're all 90 degrees, right? Segment A triple prime, B triple prime now lie on ray PQ. A triple prime B. Oh, okay. So he's saying this is 90 degrees, that's 90 degrees. Therefore, they all have to line up or be coincident. Okay, they create a straight line. Okay, and then he says reflect across PQ. I'm sorry, reflect across PS, which is right here. That'll get the purple triangle to land on the larger triangle, PQRS, which is what he wanted. Using, okay, using H prime P, okay, A, B. Wow, so this kid's really, why is he applying? So notice how he's applying scale factors to each individual line after he does like some other sequence. So notice he does that. So all right, so let me explain what he's doing because this is pretty messy, isn't it? So he's basically saying, okay, like he doesn't even get that part. I see what he's doing. So he's saying, here's my step. Okay. Then I reflect in step 4. No, 5. This is step 5. And then he says, dilate so you can get this side to move down. Okay. So the problem with this kid is he's getting very specific. In fact, you can just tell right away he's really going in depth here. So it looks like in step 4, right, when he dilates, he only dilates one side. Like he dilates horizontally. But then later on, he dilates the other rest of the rectangle vertically. So that's where he messed up. Okay, so dilations do not occur separately. Okay, in summary of this entire mess, remember how in 8.1 we had two different scale factors? That's what we are talking about when we're saying we're dilating separately. Okay, you're using different scale factors. All right, this kid right here, Tyler, he used two different scale factors. All right, so his scale factor here was PS to AD. Meanwhile, when he dilates vertically, he dilates with the scale factor of PQ to AB. That is his problem. Okay, what a mess. But it's good to see, like, okay, we can't do that. You can't dilate with two different scale factors. It's not going to work. And you can see that even more clearly in 8.1. Okay. Thank you for putting up with me on that one. All right. Always prove it. Okay. Choose one statement from the list. I'm going to do all four. Okay. Just fair warning. Decide if it's true or not. If it's true, write a proof. If it's not, prove a counterexample. Statement. All right. So statement one. Let's go ahead and do that. All equilateral triangles are similar. Let's see. Equilateral means their sides are all right. It's like a rough drawing here, so bear with me. 60, 60, 60, right? This side has to be congruent to that side, and that side. All three sides are congruent, right? Yeah, that's true. Now, why is that true? If I can show you, right? Like I'll shrink that down. Notice how the angles will still stay 60, 60, 60. And let's say this was, I don't know, 3, 3, 3, 2, 2, 2. All the sides have to be the same, right? All the sides have to be equal. Therefore, your scale factor would have to be the same for all your dimensions. So number one is true. All right. Let's take a look at number two and see what happens here. All isosceles triangle, or all isosceles. Let's see. Number two, all isosceles triangles are similar. Let's see. This side has to be congruent to that side. The base can be different though, right? This angle has to be congruent to that angle, but not the top angle. Well, immediately I can actually give you an example of where this will not be similar to this angle. Because what if, and I can draw another example. Like this could be 30 degrees. This has to be 30 degrees, right? This is 120 degrees because of that. This side could be like, I don't know, 5, 5, and I don't know, 7, right? And I'm just making it up right now. But I can totally draw another isosceles triangle where it's like these angles are much more different, right? These are like, I don't know, 60, 60. Actually, no, I can't do 60. That would be equilateral. Silly me bananas. That's actually more. That's 80-ish. 80, 80. All right, so that's 160, and this is 20. So notice how the angles aren't preserved, right? So like that's not going to be a thing. Let's say this is what's 5 times 2? Let's say 5 times 2 is 10. All right, 10. But notice how like these can be the same. The basis has to be different. But the scale factors, yeah. So this okay. So that's not going to be a good example. Let me explain it. Yeah, different angles. So it's not really about the sides here. It's the fact that, yeah, your angles, right? Like they're both isosceles, but the angles are different, right? It's not like where angles are preserved, are always preserved with equilaterals. Preserved. There we go. Right? So number 2, no. You can have different angles. They're still isosceles, but they're not similar. Their angles are off. All right, number 3, all right triangles are similar. Okay, that's definitely false, only because I know of 2 specific right triangles. I know of a 30 degrees, 60 degrees, 90-degree right triangle versus the good old-fashioned 45, 45, 90 triangle. All right. So notice, yes, they're both right triangles, but their angles aren't the same. So that's false. All right, their angles aren't preserved. Number 4, all circles are similar. That is true. All right, you got this circle. Copy, paste to this circle, but it doesn't matter. Every circle has 360 degrees. Angles stay the same. So that's true. Okay. All right, so it's really about the angles when you think about it, okay, in terms of similarity. I mean, yes, the dilation could be wrong, but in terms of similarity, it's about the angles. Okay, so in summary, one figure is similar to another if there's a sequence of rigid motions and dilations. Take the first figure so that it fits directly over or exactly over the second. Okay, and that's the definition from, I believe, lesson 6. Okay, one of your classwork questions were involving that. All right, consider any 2 circles, for example, A and B. Translate the circle. So notice how they do a translation, right? And then a dilation would make the smaller circle larger, right? And it'll fit perfectly around the larger circle that you wanted to fit around. So it actually, can I do that? Let's see if I can do that. Hold on. Ooh, that's not what I wanted to do. There we go. Oh, no, no, no. That's not what I wanted. There we go. So you're here, you dilate, and then you or I'm sorry, not dilate. You translate, right? So here you are. You translate over, you dilate, and ta-da, right? Sorry, can't, man, this thing always has to mess with me. All right, there we go. All right, so that's the end of the lesson. Have a beautiful day.